So, in these lectures, I'll going to basically cover hateful speech on social media. There are various aspects to it, so I'll cover each aspect one by one. Okay, whenever you have a doubt, you feel feel free to ask and like interrupt me anytime. Okay, so I think let me begin. How many have you heard of hateful speech on social media being a problem? Show of hands. Okay. Quite a few of you. Very good. Yeah. So I think then I don't have a problem to explain what is hateful speech, all of that. I don't have to do. Okay. So social media, how many of you use it? WhatsApp, Facebook, Instagram. Why do you use it? Anybody? Sorry? Entertainment. Okay. Anyone else? Anything else? Yeah. Remain connected. Connectivity. Okay. Anything else? Updates. Yeah. Information sharing. Okay. Any other? Yeah, there's quite a few, right? So information sharing is what social media platforms were meant for, right? So that's how they started with. So you can remain connected with other people and share the information, right? So we use social media, almost everybody, each of us, right? Every day, Facebook, WhatsApp, whatever mean of communication we use, right? But then in addition to, initially they were meant to share information, right, or remain connected. But with time, people have started using them for other purposes, right? So there is fake information, which is quite popular, right? People use it to spread fake information. And that has been like during COVID time, actually fake information was so popular, right? It became a big time problem. So fake information, then there is a hateful information, right? People spread hate through social media platforms, right? That's actually big issue. There are actively government of US, government of India, and every government in the world is actually actively working towards how we can use social media in a rightful manner, right? So that hateful news or hateful information is curbed before it sort of spreads in the network further. So there has been instances on social media platforms, especially Facebook, that because of the hateful information on the social media platforms, there were real life violence that happened in Sri Lanka, happened in Myanmar. There were real life violence because of the hateful information on social media platforms, right? So in fact, Facebook was blamed that there was a mob in Sri Lanka because of the Facebook, right? So there has been a lot of scenarios, and not only for government, right? Even for the social media platforms themselves, right? They would like their platforms to be used for benign purposes, not for fake information spreading or hateful information spreading, right? So Twitter has a lot of policies already in place, right, which try to curb, right, that this is a hateful message. Maybe they will not let you post. In fact, all of you might have seen on large language models, right? If you put some hateful words or something which is not good for the society, it will actually not answer you. It will tell that, okay, there is a hateful information, there's something which you're trying to ask is not good for society, so I will not answer. It will politely refuse to answer. So there are a lot of these checks and balances put in these platforms, but still there are people are smart, right? They will find a way to circumference or to basically circumvent these checks and rules, right? So that's why this field is still interesting, that how do we figure out what is hateful information, right? Because there are words which are actually not hateful may be used for hateful information, right? So there is a lot of work going on in this domain to actively figure out what is hateful and what is not hateful. So that is, so I will cover a few approaches today, what is going on, right, in the research on this field. And then I'll also, yeah, let me go to the next slide. Yeah. So, and but then, yeah, why do people use hate, right, in these platforms, right? So, let's say you want to post a tweet, right? You want to, of course, you want it to become viral. Like, there's people, we have that in mind, like, whatever. If I want to spread it, then I will have something, some catchy words or something interesting, then only people will further retweet. So same, like lot of people use this emotions, right? Sarcasm is one thing. Sarcastic tweet could actually usually gets more attention, right? So hey, and it is shown that hateful tweets actually gets more retweets than the normal plain tweets, right? So there is a reason to have like hateful tweets. So just to have it, like just to make it viral, that could be one motivation behind having hateful tweets. Okay, so that's why the presence of these various nuances, right, such as hate, irony, or sarcasm, makes a tweet prone to become viral. So people use that these linguistic aspects to basically enrich the tweet so that people will spread it further. Okay. So with that, so these are the various topics which I'll cover. So first one is basically hate speech detection. How do we even figure out that a piece of content has hateful information? That is the first one. Second, I will talk about the various approaches or the models which have been used to to figure out whether the hate will spread in this particular manner or not, right? So basically, hate is spread modeling, and then second topic I'll talk about is the homophilic analysis, which is basically homophily in hateful speech. So, and that's actually prominent. So that's what people have observed. There is a homophily, and then how can homophilic nature of hateful speech generation can be used to curb itself, right? So that is the second, and I think I will have time, then we might cover the life cycle. But yeah, no, these are the three mains: hateful speech detection, spread modeling, and the homophilic analysis. Okay. Okay, so there is a lot of text, but don't worry, I will not ask you to read it. So what are the various approaches for hate speech detection, right? So let's say given a piece of text, how would you go about it? Any one of you. I'll ask, let's say, whether this text is hateful or not, right? As a human, not as a machine. Forget about the machine. As a human, how will you figure out this is hateful?
For some, let's say, for example, offensive words.
Words, yeah, offensive words. That's a good one, yeah.
But like, then also, like, if offensive words is not to present in a text for it to be hateful.
Yeah, yeah, true, true, true. But the first clue is if there is offensive word or not.
But ma'am, that is also a bit dicey because, for example, an Afro-American can call another Afro-American the N-word, but other people can't.
Yeah,
So
yeah.
for them, that is okay to do that, but for other people, it's not.
Yeah, so context matters, right? That's what you're saying. Context matters a lot, yeah. Without context, just presence of few words will not determine, right? What else?
Offensive emojis.
Oh, emojis, yeah, the emoticons used, right? Yes, that's another clue. Yep. What else? Images, yes, images. Yep, yeah.
Sarcasm.
Sarcasm, yes.
There is no offensive word in it, but also it's sarcastic or directed towards someone, right? Say to a marginalized community or personally and with the.
Yeah, so often hate is expressed as sarcasm because then you can bypass.
You get like stereotypic expressions,
So it's a
stereotyping.
stereotyping expressions, yes. Yeah, the word, the phrase is right. Let's something is used for use. The phrase, yes. What else?
Targeting a particular community or religion.
Yeah, so that's the kind, yeah, that's a religious, yeah, the communal hate. Yeah.
Maybe from the context, like let's say an opposition party is writing something about the other party, we can, without even reading, we can assume that
Yeah.
they are writing something about them. It will be.
Yeah, that's true. BJP saying something about Congress, right? They will not say good things about Congress. Yeah, so that's again context, right? So we know these are two opposing parties and they will not appreciate each other. Okay. Yeah, so there are a lot of, yeah, that's how hateful speech detection is started, right? Using the NLP part. Now, I don't know how many of you heard NLP word?
Heard about this, but not really.
Yeah. NLP, natural language processing, right? Basically parsing the text into something which a computer can understand, and then we can use that information for doing various NLP tasks, right? So that's how hate speech detection is started, right? So given a piece of text, people have basically will parse the text, right? So like you said, presence of certain words, right? That is one feature, right? So that the presence of certain words or phrases is one feature. So that's how they will derive the features out of the text. So that is basically your plain old vanilla machine learning where you are constructing features, right? So like when you construct features, let's say you have an image, fish. So when you do classification fish or not, you will have features for fish. This is how fish looks like. This is how fish doesn't look like, right? So those features will tell you. Then you'll have enough images of fish to learn that this is my fish. This is not my fish. Okay. Similarly, this is how it is started. Binary classification, right? This is my hateful content or not. So you have a text. Now from the text, basically figuring out what are the various features, right? Now what is important? Which features, right? So features, that's how the traditional machine learning has been. Deriving important features is the main key part. So if I have features which are relevant for the problem, then you will have a good solution, right? Because model is fixed. A model you can vary a little bit here and there. But main important part is basically features, right? Feature engineering. That has been the biggest part for machine learning, solving machine learning problems, right? So here again also the researchers started with feature engineering. What features are important? So phrases which are, and phrases, right? They have basically a list of, you can bad words or phrases which are used in offensive manner, right? Or in a hateful manner. So there is a one list is publicly available. So there is one list of words and phrases. So presence of those words, how many times, right? And if you see in the text, right, when you write in capital, you want to convey something different, right? Punctuation marks, right? So exclamation marks, lot of exclamation marks mean something. So that's how they were deriving features, right? So is there a capital letters used, right? Though may not be relevant for only for hateful in general, right? Something special about a piece of text is basically, are there capital letters? How many words you have used, right, which are in capital letters? What are the various phrases which have been used? And then the diversity in the words, right? If you're repeating the same word often, maybe there's something about it versus you're using very different, like lot of different words. So all of and this list is not fixed. You can, depending on you can customize the features, come up with your own features, right? So that's how NLP started with, right? So you basically design these features. So that's how for a hateful speech also. So these researcher, I have these references in a separate deck, you can have it, right? So all these researcher basically crafted these lexical features, lexical and linguistic features from the text. So they have a certain text which is hateful, there's certain which is not, right? So they have both the classes present. So hateful text, non-hateful text, sorry. Binary classification, so they have these features designed and figure out the features and then build a classifier. You can use any regular, like logistic regression, SVM or any other classifier. Okay, and so but then in the first set of works, right, they were not worried about, see, hate and offenses, there is certain difference, right? Offense need not be hate. So there's how this second set of people came, right? Okay, there is a, it's not so easy as we say that hateful speech detection, but then there are certain nuances we should be taking care of, like offense and hate should be treated separately. So that's how they had they yeah, the first, I think I should talk about. So the first thing is, I told that you have to have data, right? Label data, label text, which is hateful and non-hateful. But getting that text, where do we get it from, right? So that any machine learning, data is a big problem. So, and getting label data is a huge problem. So this is the first work by these guys, Davidson. So they actually collected a few number of tweets, around 17K tweets, and then they went to this crowdsourcing tool and asked people to annotate with these labels, right? So hateful, offensive, and none of these two. So these three labels, right? So they wanted to keep offense separate because offense and hate is different. So that's why they have a third label which is like offense. And And now then again, data labeling, even you have humans to label, right? Human have their own biases, right? So they ask humans to label or annotate these tweets from using this mechanical Turk, right? The crowdsourcing tool, and then and that's how the first set of tweets were collected, which were basically were labeled as hateful, offensive, or not. Huh.
Explain the difference between hate and offense in a more.
Offense could be, let's say, any insulting remark could be an offense, right? But it need not be hate.
But this barrier will depend from person to person, right? Who think what is offensive and what is hate speech.
It depends on person to person, yes. But then see, hate, when I say, let's say, so Jews, right? One example. So there was hate against Jews in Germany, like World War II happened. We know that. That was hate, right? Kashmir violence happened because that was hate. So there is like hate is this bigger, I would say bigger impact. Offense could be just one person, right? It's just it doesn't impact every people of certain religious
More targeted towards a larger community.
larger community in general. Offense, and then the implications are different, right? Offense, I might feel bad, right? But hate is a different implications, right?
Always targeted towards a community.
Yes, so hate is targeted towards a community. So I'll talk about various kinds of hate, right? So one is, let's say, racism, right? So which is in US, which is is a common problem, right? Black versus white, that's a common problem. So racism, right? Then you have religion, right? Then you have xenophobia, homophobia, right? All this basically targeted towards a community. So in general, yes.
So, in that one of the papers by P.B. Matthews, they had cited a paper, I forgot the name, but that paper essentially says that they did a qualitative analysis of hate and they defined hate as a direct and a serious attack on any protected category of people based on their race, ethnicity, national origin, religion, sex, gender, sexual orientation, disability, or disease. So that can be broadly understood as hate. Offense could be something like if someone says I'm stupid, I take a offense. So that could be
Yeah.
offensive, but this is not necessarily hateful, right?
Yeah, yeah, thank you, Atman. Okay, okay, so this is how hateful speech detection started with plain vanilla machine learning, feature engineering based approaches. Later on, with deep learning, right? So people started using the embeddings. So we have word to vec word embeddings came, right? Then many other embedding approaches came, right? Better, right? Word to vec is the first, right? Word embeddings where basically you have which captures the, so word embedding captures semantics of that word also, right? The surrounding words. So then basically in another work, right? So these guys actually trained their own word embeddings for the in the case of hate, right? So they had their own word embeddings, and then they use a regular classification model to detect hate. Right? Okay, so yeah, I think we can go to the next one. Okay, yeah. So I think what you guys were also suggesting, right? So just use without context is difficult to say this is hate or not, right? So without context is especially on Twitter, right? There is a lot of because you have certain only limited number of characters, right? 140 characters, so you cannot have the entire context. In fact, certain times, right? Like what you were saying, context is in the image because there is a text and then there is a link to an image. So link the image is actually has the hateful content, not the text. So and that's what actually the word is going to towards multimodal, right? We have ChatGPT 3 and ChatGPT 4, which is multimodal. So just alone text is not sufficient, so image should be considered. But in these works, initially people were only doing text, right? So there are, of course, it's not 100% accurate. So there are accuracy compromise happens, but then yeah, you live with that, right? What to do? Okay, so so there is so basically all this paper says that context is important. Even benign words can be at times used in a hateful context, right? So if you don't look at the context, it's hard to figure out whether it's hateful or not. Okay. And so yeah, so in these papers basically they're saying that multimodal hateful speech detection, where they're taking into the socio-political context to improve hateful speech detection. And then there are papers around context aware models. And okay, so with that, yeah, I think I'll talk a little bit more on this one, right? Because this is a social networks, this is a networks course. Okay, so far we only spoke about the text. Okay, text is important, but one thing which I've missed is basically the user who is writing. Yeah, that is important, right? I am writing versus you are writing versus anybody else is writing, right? Will matter whether this text is hateful or not. Trump writing versus Narendra Modi writing versus somebody else writing, right? So who you are actually matters when we figure out it is hateful or not. So that's where there are few papers, right? Few initial approaches. The field is still open, and people are working in this field. Is basically use the social aspect. Who are you? And what is your neighborhood? Who are is defined by you as a person and your friends, right? Friends, relative, or your colleagues, whoever. So basically, you as a person, in addition to your social network, the community you are part of it, right? So that's how these few approaches have they have tackled this aspect, the social part of it. So how do I figure out who am I, right? So what I write, that my profile, okay, I have my profile information, and who are my friends, right? But then I know, but how do I encode this information, right? Text I know how to encode. I derive features out of the text, right? But how do I encode this who am I, right? So I use graph, right? That's how. So I am connected with these people. I know the strength of the connections, right? I know that edges, right? I know the frequency I connect, or maybe from tutor you can derive, right? So all of that information I use to encode me, or to encode you, right? So who are you? So I encode you using your friends, your profile information, and your activity, all of that, right? So that's what I do to encode you. Okay. So this is how this first work started, right? So they basically they all, in addition to the NLP features, they also included the network feature, the social network features, right? So where, let's say, only 3 node graph, right? And you are in the center, 2 are connected to you. You are sort of important in a way, right? So your position in the network, connections in the network, right? That matters. So what they basically derived a few graph features from the social network. So now what are these graph features? Simple, right? Could be your in degree, your out degree, how many people you're connected with, how many people you are connected to you, right? So incoming and outgoing both. And then how basically, what is your betweenness, right? All the centrality which you can think of, right? Betweenness, closeness, right? So, and especially on Twitter, right, there's a concept of, right, I am following, are you following me back, right? So all these social features, right? These are the features. Actually, yeah, we have a tutorial on this one. So you're going to derive these, infer these features for in the tutorial. So what are the various features which can be important, and which you should think, right? Which are more important for a person? How do I encode this person, right? Given the position of a person in the network, right? How do I encode it properly, right? So that I capture all the nuances of that person, right? So that's how they started with, right? So they used a few basic features, and then they build a basic logistic regression classifier to do binary classification. Okay. So I think I'll talk about this in detail, and this is tutorial also focuses on this particular paper. Okay. So if you see, so this is I think this is sort of important paper, also important approach, right? So where basically they're combining these two modalities together, the social and the text, right? So text and together. So they have in this is a, I don't know how many of you are aware of, have you heard of deep learning? No, not very familiar with deep. Okay, okay. No worries, no worries. But yeah, so basically what you can see, right? Um, so there are two modalities we have. One is the text, another is the graph, right? In your let's go back here. Like with the first approach we started with, right? In our traditional machine learning, right, we see there are features, right? These features we derive, infer, right? So when I from a text I'll see, okay, this word is present or not, right? How many capital letters, how many emoticons used, right? What type of emoticon used. I'll create a feature set, and basically for each my sample I'll get those features, right? And construct that data set. And I will do this for both the classes, the, the positive class and the negative class, hateful or not, right? So this, and then you have a machine learning model to learn with. Now, okay, now with deep learning, okay, so now with deep learning is basically learning like your traditional learning only, but slightly different. So people is okay. So now in the traditional machine learning, you need to know which features, right? You have to come with yourself. So these are the features I will. This is important feature because of I think this is important, or others think because this is important. But then how do you know this is important, right? So that's how much deep learning is started, right? Basically, I don't have to worry about the features from the text. Let the machine learn itself. Okay, let the machine learn what features to infer, right? So that's how, if you see, I think that classical example, cat or not, right? So how the features of cat, the machine will learn, right? So this is how the cat looks like, versus this is how it doesn't look like. So these features, right? So they are learned automatically by the model. And if the model has to learn these automatically, it has to be big, right? It cannot be small because it has to learn so many things. Otherwise, it will overfit. I don't know, you know, overfitting. Yeah, basically, the model only works on the data it is trained on. It just learned whatever. If any new example given to it, it will not recognize or will not do well. So this is how deep learning started. That can I encode the features automatically without worrying about the features. I don't have to do myself manually and automate. So in all of, so then image classification, text classification, like BERT came, all of that, word to way came. So they were basically deep learning models. So they learn features from the words without me telling, and then do the task, the classification task. Okay, I'll know. I think, yeah, I can go into details of deep learning, but maybe in the interest of everybody, it is not needed now. But if required, you can later ask me. Okay. So now what these guys have done, so they have text input, and they have another input which is metadata. So metadata captures three different types of data, which is basically there are certain features they derive from tweets, certain features they derive from user and network, right? Social network, which is the main focus. So so from the tweets they basically yeah, so from the tweets they will count. They have these various features which we spoke about earlier, right? So is there a particular emotion present, anger, disgust, fear, joy, all of, or there is offensive words used or sentiment used, right? All uppercase, right? And the number of hashtags, all of those, right? Those are the features. Then the user features, right? User features is basically, I talked about in degree, out degree, which is a number of followers, number of followees, right? In case of Twitter. And then activity, how often do you post, right? How basically whatever you do on the social network, right? Then your network features is basically is reciprocity, right? I follow you, are you following me back, right? So that shows my importance in a way. Then how centrality scores varies, like eigenvector, your betweenness, closeness, clustering coefficient, all of those, right? So then these are the various features they have used, and then what they did is basically they encoded these two information separately. So there are two parts, right? The first part is, yeah, this one I can use, right? Okay, I'll use. Yeah, so this is the first part, right? In this part, right, they're basically encoding the text, and the text is encoded using this RNN, which is a type of a recurrent, which is basically a deep learning model called recurrent neural network. And yeah, if you want to know more about, you can read about, or you can ask me later. So this is the text is first passed through an embedding layer, which is basically gets the word embedding of each word. Word embedding is basically n dimension vector for each word, right? That's what embedding is. And then this embeddings are passed through. So for the whole text, right? So there are let's say 10 words, you will have 10 embedding vectors. So Atman will talk more about it when in the tutorial. Now these 10 embedding vectors are basically passed through this RNN layer, right, which is a recurrent neural network. And at the end of the day, what you get is basically a 128 dimensional vector, right? That's the encoding of the whole text. Okay. And on the right one's right side, right, this one, this is basically the metadata input, right? So you do normalization, then those layers are basically your regular deep learning network, right? So perceptron kind of network, right? So you have a fully connected layer, dense layers, all of that, right? Then finally, at the end of the day, what matters is this output right here. So this output and this output, both are connected, right? So both are basically then concatenated with each other to get one vector for the whole tweet. So now this one vector has information from the user, right? From the text and network, right? Everything put together, and finally the classification layer, where basically you do the classification, regular classification, hateful or not, right? So that's the thing, right? So this is like one of the sort of first approach which tackled, right, can we use the social features, who are you, and you encode that information and use in the classification finally. Okay, okay, so here so there are basically the work I have been doing, right? So especially I have been working in the social aspect part, right? So I have few approaches where I have used the social part, right? The social aspect to improve hateful speech detection on Twitter, right? Tweets, right? So there is two papers. In the first one, we will talk about the user aspect, right? And so sprayed one, and the second one the user aspect. So in the sprayed one is basically it tells, right, that if something is going viral, right, there is something special about it. Can I use that information to figure out what content it is, right? So I use the spread part of it to figure out what it is, right? That's the first part. The second part is basically, so I say that this I'm using these network features, right? I am using your centrality scores, I'm using your in degree, out degree, all of those. But that doesn't give the whole picture, right? Where I am, how far I am from everybody, what is my position, what is my location in the network. It doesn't give you the entire picture. It gives some picture, of course, but it doesn't give the whole picture. So that's what I will talk about in the unified representation of a user. How do we get this whole picture of a user, right? How do I get an embedding of a user, encoding of a user, so that I capture this, the whole aspect? Okay. Okay, so this is the first one, right? So let's go to the multitask. So that's where basically the title is affect. So here affect, there are two linguistics part, I would say hate and sarcasm. Okay, both I have done, and in a multitask setup, right? So if I was sprayed, right? So if I can use the information from sprayed in the classification task, I'll be benefited, right? Because I know this tweet is viral, this tweet is basically has gone so many places. I know something about that tweet. Can I use that for my classification task, right? That's what. So that's what we have done here. So here, yeah, I think this can be skipped. I'll just, yeah. So basically in this, there are two tasks. One is the main task is basically your hateful speech detection, the classification, that's the main task. There's one more task we have is here is the, we call it auxiliary task, which is your retweet count prediction, which is a regression task. So if retweet count is more, that means the tweet is more popular, right? Versus if the retweet count is less, the tweet is less popular. So that's what we use, right? So there are two tasks we have. The auxiliary task helps the main task, which is basically the classification. So it's basically marrying these two tasks together, sharing information from each other to help each other, right? So that's what we have done. So now, and in fact, so at the training time we need, right? So because there are two tasks, one is the regression and the classification. Yeah, how many of you know regression? I've been talking about regression. All of you know. Okay, nice. So then, okay. So in the regression task, we are predicting the retweet count, right? In the classification task, we are saying hateful or not. It's a binary classification, right? And so at the training time, we'll need both the information, right? For a tweet, we know we need the label, is a hateful or not. We also need the retweet count. And at the inference time, at the time of prediction, we basically need the tweet text. And using the tweet text, we can predict the retweet count also and the classification also. So like both, it's like killing two birds together in a one shot, right? So at the retweet, at the prediction time, you know this text is hateful or not. And well in advance, you can also predict whether this text, what will be the retweet count, whether it will go viral or not, right? So that also you can predict. Okay. So what are the input, right? So basically, again, we have used the tweet text which everybody is using, and then certain metadata based, certain meta features, right? Which is coming from the tweet features, whatever basically same set of features, right? So count of emoticons, words, uppercase, right? Presence of certain words, all of that, right? And then user based features, which is basically captures user information. So this is their profile information, their follower friends count, right? Tweet posts, how active you are, your favorite tweets count, how many lists, subscribe list you have, all of those, right? More like whatever activity you are doing on the social network, that is captured. Okay. Okay. Now, so these are your features, right? Your text input, this side, and your metadata input. It's sort of same architecture we saw just now, but slightly different difference at the end where we have two tasks, right? So we have text input coming from the tweet text, and we have metadata input coming from the users from the tweets, right? So these are human derived manual features. Okay. So on the from the tweet text, we basically get the embeddings, right? So you can use the different ways, right? The word to wake started, then the glove embeddings, now there are fast text embeddings, now bird embeddings. So basic is off the shelf. You can get any existing trained model. So fast text embedding are nothing but embeddings or word vectors for each word, right? So these you have in this layer, right? And then is yeah, you need little bit of deep. So this is basically a deep learning model. So there are some layers, right? So multi-head attention is basically kind of layer, right? So that's a multi-head attention. Then LSTM, I think Atman will also have LSTM in the tutorial, right? So LSTM is again a kind of recurrent neural network. You don't have to worry about, these are like the regular building blocks of a deep learning network. So these are the various layers. So a deep learning network has layers, right? You can stack these layers in a different manner, the way you wish, and how many blocks you want, that is also configurable. All of that you can try. So each of these block, right? You can have multiple of these layers, right? You can have multiple of this layer also, right? So all those are the things people try when they build a deep learning model. What are the number of layers I should be using? What are the various layers I should be using? So this is one model on the left side, right? That's basically will give you a a representation of the text at the end of the day, right? And on this part, right, this is again a deep learning model, right, where I'm capturing the representation of the input, which is the metadata features, right? So the metadata features, this is again one layer, right? This is dense layer, dense layer, dense layer. Basically you are reducing your features to 512 to 250, 256 and 128. I think this is okay, but what is more interesting is the central part, right? The central part says that this is the shared information. So I am using, so representation of the text is going here, representation of this metadata is also going here. So both are put together, and this is again another deep learning. This is a DL model, right? These are the deep learning layers, right? So layer meaning there are parameters, you learn those, right? It's basically model. So model has learnable parameters. Well, parameters will learn how this object look like. That's what. So these are, so basically this, the shared common representation is learning what is common between the two. Okay, and that shared common representation is again passed to both the output, right? So here, so the first is basically classification, right? Second is the regression. So we have classification output and we have regression output, right? So this is the important part, that we are learning, sharing, they're sharing. So I am learning whatever information I could do from the regression task, from the retweet count, and I am learning also from the text. And the common information between two is shared across, right? So here now basically your task is that given a tweet, this is the what is the whether it's a headful or not, and what is the retweet it will gather, right? So that's the inference you will do. So given a tweet, I want to figure out whether a tweet is headful or not, and what is the retweet count. So at the time of training, you will basically train this network, right? The whole network will be trained, and basically you will say, okay, this is my tweet and this is my retweet count and this is my whether headful or not, that label, and you will train the whole network, and at the time of inference you will figure out whether a tweet is headful or not, what is the retweet count, right? So this is leveraging these two together to do better in both, right? Better in retweet count prediction also, better in the classification also. Okay, so these were, I think these are the two data sets we have tried. So there is this is the same data, right? So we have hateful, abusive and normal tweets. And then there's another data is a sarcasm detection we have tried, right? So in this, in the first data, there are 53K around tweets, and then out of those, see 27% are hateful and rest of them are normal, right? So this is the data you're dealing with, and basically we also need to get what is the retweet count, that there are Twitter APIs available. You can use those APIs to get the retweet count, a user profile information, all of those. Right? Okay, so here, in the experiments, basically we created features for the tweets, user features, right? Tweet features, again the same set of features, and then we train this whole network. So basically for the classification, we use a cross entropy loss, which is quite common, right? And then for the regression, this is the mean square loss, right? And then the regular split, right? And basically we wanted to see, right, how does it perform with respect to baselines. So there are these 4 different baselines we have tried, right? So the first baseline would be what happens if I remove this right part? If I remove this part, if I only do this one, right? This first part, what happens? Are these features really useful or not? We are saying that these features are useful, this common representation useful, but what if I get rid of it, right? That's the first baseline, and then basically you can also have just the naive based model using the TF-IDF weights. I don't know TF-IDF, you guys know?
Like in information like
Term frequency. And yeah. So it's basically to be in a layman terms, like frequency of words, score for each word, TF-IDF, like a score for each word, right? So using that I build a naive based model, and how does that perform, right? And then you can also have a just a separate regression model for the retweet count prediction, right? That's another baseline. And then you can also have, right, we can get rid of the, so fast text is basically your, it has the context, right? Context in the embeddings. So you can try with, let's say, word to wake, glove embeddings, what happens, right? All of those options are feasible. So these are the baselines, and yeah, these are the results. So it seems right, the multitask, right, which I described, works better, right, because we are capturing both the task, right, both the information from both the tasks. Okay, so so far we saw that we can use the social aspect, right, the spread aspect to improve the classification task. Now and then I also talked about, right, that user features, especially who are you matters, right. So that who are you is what we'll talk now, and who are you, how do I encode that, right? That is the crux of this work, right? So how do I encode who are you? So who are you is basically we going to encode through the graph convolution networks. I think all of this, yeah, we can skip. Yeah, I think, yeah, I can show this figure again. Yeah. So here, yeah. So in a regular, without looking at who are you, without looking at the social aspect, just looking at the text, right? This is how people do it, right? This is how people have been doing, right? So let's say you have a tweet, you won $5,000. So what you'll do is basically LSTM is that recurrent neural network, right? Is a type of a recurrent neural network. So you will get embedding of you, right? This is the first embedding. Then you will get embedding one. You get this embedding, and the recurrent neural network basically the main yeah, property is that you pass output of previous step to the next one, right? So here you embedding of you after doing some operations here is basically passed to the next layer, right? So when you are encoding one, right, you already know there is a U in the front, right, because it has been passed here. Similarly, when you're encoding this $5,000, you already have the encoding of these two combined, U and 1, which is basically coming from here, right? So now, after you've done this for all the words, the final encoding will give it to a softmax classification, which is like binary classification, right? So this is how the regular architecture have been. Okay, and basically the changes you can do is you can try different things here, right? That's what you can do. You can use transformers, you can use LSTM, you can use gated recurrent units, whatever, right? Basically different models you can use here. And then you can also try different embeddings here. So that's how, these are the two places where you can try multiple things. Okay. So now what we saw earlier, right, that from the graph we inferred a few features, which is basically my neighbors, count of my neighbors, my centrality score, right, my yeah, my popularity, all of that, right. So here what we are saying, that rather than figuring these features manually, right, that's how deep learning started. I don't want to create the features manually. So here also same principle. So rather than creating who are you manually, I want the machine to create. So I just want the machine to give, I'll give the whole graph, what you've done, your all the entire activities, and now I want the machine to create who are you. So that's what we're doing here. So there is a technique called graph convolutional network to extract these features automatically. Okay, so maybe you don't have to know details of how GCN works, but then thus is just basically deep learning way to encode a graph, right? And that way you can capture the entire graph, right? So my neighborhood, their neighborhood, right? So it can capture the representation of a user automatically using graph convolutional networks. Okay, so I will, yeah, talk about this a little bit. So here again, so on the top, this is the text, right? You encode your text, and these are again a few deep learning layers. Okay, on the bottom, this is so we have basically using GCN, we have trained, we have learned what a user representation is, right? This is a sort of, you can imagine it's a black box for you, and using GCN we have learned what user embeddings are, and then we use those embeddings, right? So it's basically this is pre-trained GCN, and then we have graph, basically graph embeddings from GCN. We get the user embedding, and these are the two inputs, right? So you have text and you have user representation, and then this is like concurrent, put them together, and finally a few fully forward. These are again few deep learning layers, right? And finally this softmax binary classification. So that's how this architecture looks like.
So it's something similar as to what the architecture you showed previously, where we had that RNN on one side and other social
Meta features on the other side, yeah, yeah.
we have a GCN and
This we have a GCN, yes, yes. It's basically only this much difference. So the GCN features, and the GCN features are basically coming from the entire graph. Okay, yeah.
sorry to interrupt, but this GCN is usually pre-trained on what type of data, like
Yeah, I'll talk about little bit about this, yeah. Okay, so now GCN is basically graph convolutional network. So GCN has captures two parts. One is the graph, and another is the user, right? So when we learn GCN, we give one is user feature matrix, another is graph adjacency metric, right? These two together, imagine these are like your one big matrix, right? Feature matrix. If there are n nodes and there are m features, you will n cross m one matrix, and there are adjacency matrix or n cross n. These are big matrix, right? You want to encode these two together, right, to get a small representation of a user. So that's how through convolution we do it. I'll show you how does it work, right? So yep. So here is the, yeah. So basically, yeah. So this is your user feature matrix, right? So n cross, let's say L features. This is your adjacency matrix, which is n cross n. And now, how do you learn, right? When you learn, let's say you're learning this is a cat or note, right? What you know that these samples are corresponding to cat class. These samples are corresponding to note cat, right? And then you tell your model, these are my cats, these are my not cats, whatever, right? And the model internally will learn a representation that this is how cat looks like, and this is how cat doesn't look like. But so in this scenario we have labels. So for a sample we have labels, but in a graph, right, I want to learn a representation for a user. I don't have label, right? How do I learn who are you, right, without a label for you? So that's where this autoencoder comes into picture, right? Autoencoder is basically, it's like encoding you. So whatever features I have for you, I learn a small, I mean, let's say I have a middle representation, the small, and then I sort of construct back who are you, right? So I'll here, so in the encoder part, what happens? Basically the features are given and you get a small representation, right? In the decoder part, what happens is Z is given and same input is reconstructed. That way is a label, right? And then what you minimize is basically what I have reconstructed is same as what I have given. That way you can learn, right? You don't, so let me repeat, I think this is when you are learning you have when you are learning you have labels, right? So you learn in that context, in the context of labels. But when you don't have labels, I want to just learn the representation of let's say I just have cats. I want to learn how cat looks like, right? So what I'll do, okay, these are my cats. I'll learn a representation. Basically, I have a small representation, and from that small representation, I again create big representation, right? And this big representation, is should be same as what I gave, basically the same. So then I am minimizing that what I gave is what it should come back. So that is the loss you minimize. Maybe a bit too much, but yeah, I will, is basically you are creating the same input again, and now so when you learn, when you do classification, the loss you minimize basically the label and what you predicted, right? So that's the loss for you, and that's what you basically optimize, right? And here the loss is basically I want to create the same image again. So that, and what I created versus what I gave, if they are same, my loss is minimum, right? So that's the concept of autoencoder. I'm encoding this input and I'm basically automatically doing it by using the same input, right? It's called autoencoder. They are quite popular these days. People use it in various contexts actually. So it can be used for compression, right? If you see, in the middle we're basically compressing the input. So it has been used for compression related task also. So what we are doing in our case, so we have a graph, the adjacency metric, we have user feature metrics, right? So we encode and we get this latent representation, see, we again decode, right, and basically we minimize this. So there are two losses in the process are minimized, cross entropy loss and the KL divergence, but we don't have to go in the details. So now what we are creating again is the adjacency metric, same adjacency metric we gave, right? So that is what we are doing. So this process is called autoencoder. Now you is same, you graph or node doesn't matter, is basically autoencoder. In our case we have used graph autoencoder because we wanted to encode the graph, the user. Okay, so this is what we have used. Okay, so now if you see, there are two things needed here. One is the adjacency matrix, we have that already, right, from the graph. Another is the user feature matrix, right, because we want to encode the graph part and the user part together, the user from the profile information and other things, right. So these are the two inputs needed, this one and this one. So we say that we construct the first one, the adjacency matrix we have, but the first one we need to construct. Okay, so we are basically, for the first one we get the user features, right? So the user features again we infer from various sources. One is the profile information, right? The number of posts a user is making, all of that, whatever activity a user is performing, right? So that we do, right? Okay. So basically we can we've, and now we also wanted to extract the language feature, like what kind of a language a user use, right? Because that also is helpful in determining helpful or not. So the language features, so basically for what we do to get the language features is so we, whatever posts, whatever tweets you have done so far, right, that will tell you what kind of language you use, right, your style in a way. So style matters. So that's for using, for that what we do is basically we get all the tweets, right, whatever we have, and then we create a document which is one big set of like words or sentences you have posted, and then we use word scores, right. So this is TF-IDF is one way to do it. You can use any way of getting word scores, right. So that's how we get the user language feature, right. And then this, so we have basically textual features from the content, and these unified user features will have the social network feature, the language use, and the metadata, the profile information. So we are basically, these are the two types of features we have: textual features, unified user features. Unified user features further have these three types of features: social network, language use, and the metadata. Okay, so now I think, yeah, we can go into the, yeah, the experiments, right. So there are two data sets. So this one I think I have already spoken about. So this abusive and hateful data is basically the same data set, right, where the first one, right, where they manually annotated. So this is the same, this is the first data set on tweets where people have used the crowdsourcing tool to get the labels, right. So that's the first data. Now there is one more data. This is actually interesting data set, this Ribeiro one, right. This is a, I'll talk a bit more in detail on this one. Okay. So, yeah, so in the first data we already have the labels, right? Now what we do, we also get their tweet tags, profile, previous tweet, follower network, right? From tweet that you can get from Twitter. And in the Ribeiro data set, what these guys did is like, yeah, this is, so they figured out few users, right? And they got their neighbors. So roughly around, this is I think 100,000 users they have, right? Now for these 100,000 users, they basically mined their 200 most recent tweets, right? So they have now around 19 million, which is huge number, 19 million tweets, right? So it's a huge number. Then what they also have done is they have constructed this retweet graph. The retweet graph is basically, if I tweet your tweet, there is an edge from you to me, right? Because I am retweeting your tweet. So there are various ways you can create a graph among the users, right? So I know you because you are in the, we're in the same batch, right? I know you because we are from the same town. I know you because so many factors. There are different ways, and that's actually good idea when you do any graph related project, that what are the various ways I can create graph among the entities, right? So these are my entities, how do I create a social network among them? Okay, so this retweet is one common phenomenon on Twitter, right? I tweet your tweet, that means you, of course I'm following you, I might not actually, but whatever you are tweeting is interesting to me, right? That's why I'm retweeting your tweet, right? So the retweet is basically, I retweet your tweet, you retweeting his tweet, right? So there is edge from me to you, you to him, so far and so on. So there's a huge graph, right? So they created this graph, and then what they also did a crowdsourcing task. So far the labels were whether a tweet is hateful or not. Now what they did is basically they annotated users, right? So out of these users, 544 users are actually labeled as hateful based on their 200 tweets. So what are the fraction of those 200 tweets which are hateful? So based on that, these users are labeled as hateful or not. So this is the data they have, right? Okay, so with this data, the now for our task, right? The problem is that they don't have labels per tweet. They have only a certain users are labeled as hateful, but not, we don't have the labels at the tweet level. So what we did is basically we did sampling, right? So we wanted to label some of these tweets, right? Because labeling 19 million tweets is impossible. So we wanted to sample at least few thousand tweets, and then a few of my students, three of my students actually annotated those. So we sampled 30,000 tweets out of this 19 million, and then we manually annotated three different annotators for each tweet, and then basically we whether we accept an annotation, right? If there's a kappa score, there's a basically a way to capture, there's an agreement between all the three annotators. If there is enough agreement, then we accept that annotation, right? So here, sorry.
To argue on annotation, do you generally take a majority or
Yes, yeah. So now, yeah. So then, okay, yeah. So basically, there was a manual annotation carried out for the Ribeiro data set, right? So we have 30K tweets from the Ribeiro data, and from the founder data there were 43K. Because remember, there were around 55, but few of the tweets didn't exist because you can delete. So there were a lot of tweets were deleted. So now, out of those 50 something, there are only 43 finally. And this is the percentage of hateful tweets, right? That's 27. This Ribeiro one had lot more hateful tweets, because remember there are, so okay, the way we sampled those 30K, right? It's not random sampling. So what we did is basically these 544 users, right? They are included, right? Their tweets are included, their neighbors are included, right? And their tweets are included. So that way we know that the data we are annotating should have enough hateful. Otherwise, if there are no hateful, we have to again repeat the annotation process. So that's how we sampled. And there were some other criteria also. Basically, the tweets like should be greater than certain length, because short tweet will not have much information, right? the other criteria around NLP aspect that we did. So after that, we did this annotation, and yeah, we have this data. Okay, so yep. Okay, so now basically again I think so we are proposing that if we encode a user using the whole graph, we should have better performance, right? Classification performance. So that's the first hypothesis we are making, and we need to prove it with the real data, right? That's what we. So this is the first. This is the approach, and then we compare with some baselines. Basically, what if I get rid of this whole thing? Let me go back. Yeah. So if I remove this part, right, I only, yeah, the same thing, sorry. I use the only this top portion, which is basically using the text, right, what I get, right, that's the one baseline. And um, then the other various, like the only using text, using naive bias, all the other baselines which we have done earlier, right. And now the other okay, so the other thing we wanted to see, right? So we've been saying network features helps, network feature helps, but is that network features, are they correlated with performance or not, right? That's what we wanted to see. And then another is basically the length of the text, right? So how does the textual length matter? It's basically is like all of you saying context matter. With the short length, context is difficult to encode, right? So longer a tweet maybe is better, is it we can better classify it, right? So these are the two data set, and baseline A basically, yeah, baseline A is the one where we are removing the the metadata layers, right? So maybe I can go to these graphs. Okay, so Amit, when do we break?
We break it about 12, anytime between 12:15 and 12:30.
12:15 and 12:30, yeah, okay.
But you can make, do whatever is comfortable, whichever you think is the logical point.
Yeah.
If it's before 12:15 is okay, if it's after 12:30 is also okay. These people are quite nice actually.
Okay, no worries, yeah. So so in this yeah, so in this graph is basically on the x you see the eigenvector centrality, and on the y we have the accuracy coming from the classification model, right? So basically what we are saying, and then the color, the data set 1 and data set 2, right? So black is one, data set 2, which is the Ribeiro one, the second data set, right? The first is the purple one. Now just to make it crisp, right, is basically saying that so see, accuracy is going up as the eigenvector centrality is going up. So this is your accuracy curve, right, for the data set 1, and this is the another one, right, for data set 2. So it means, right, that graph features, the eigenvector centrality is high. When nodes which have high eigenvector centrality, we could classify their tweets better, right? We could so when we use when we have used the graph information also, that internally have captured this eigenvector centrality as well, right? Because we have used the GCN based encoding of a user, which have captured the everything about that user in the graph. So as the eigenvector centrality is increasing, we see there is an increase in the slight decrease, but more or less is more on the upward side. So here there is a clear upward trend. So that means graph features, right, does help, right? So high eigenvector centrality actually helps in better classification, meaning people who have high eigenvector centrality, maybe they are actually it's not, so there is one paper, yeah, which basically talks about that people who are hateful are not in the at the periphery of the network. We usually think that the people who are hateful will not be central, right? They may be at the maybe lonely nodes, right? But that is not the case. They are actually central in the network, very well connected. So which again, this graph again proves that, right? So, and this clustering coefficient is another graph, right, where we basically measuring performance or accuracy with the clustering coefficient, right? So somehow here there's no, I mean there's slight trend but not so clearly visible, right? Okay. So But there is a actually, I think this has already been established that, so we have as in this plot, right? So we have basically the length, right? Length being the tweet text length, right? How many characters, how many words, right? So that is the text length on the x-axis, text, the length of the tweets, right? On the y we have the accuracy again. So what we are saying, if you see this number 5 is basically what was the performance of the classification model for the tweets of length 5? Just 5. 5 meaning 5 words. 5 words, yes. So how tweets of 5 words length, what was the accuracy, right? That's the this curve will tell, right? And then basically there are two approaches, right? Two baselines we have, right? One is we are no this red is where we are using both the feature LSTM, basically the text feature plus the GCN, the graph features. The lower we just have the LSTM features, right? Only the text features, right? So of course, as we expected, the red is higher, right? Red because we have both features together, right? The GCN, the graph features and the text features. The blue curve is down, which is basically the text features, right? But what is more interesting is this one, the length. As the length is going up, the accuracy goes up, right? It dips a little bit further down, but initially is going up, right? Going up. So that means with length, right, as you have more context, more and more context, with bigger length you'll have better context. So your classification accuracy should ideally should also go up and is going up here also. And this trend is even more there in the case where we have both LSTM plus GCN, like we're doing better there. Okay, this particular data set, right? This trend is not so much visible, I think, because there is a reason. So in this data set, there a lot of pre-processing was done on the tweets. The tweets were truncated already, so that's why this is not such a that because the tweets were truncated, a lot of words were removed. There a lot of pre-processing was already done. That's why you don't see this trend here in this data. But in general, as the length is, but there is a tipping point, like we say, beyond a certain length, it is start confusing the model. So it's not that to keep increasing the length, the model performance will keep going up, right? It doesn't, because it's certain, beyond a certain point, right, it starts going down, right? Because certain words, then it's start getting confused with more words, right? So that's, so yeah, there is a sweet spot in between. Okay, so now so basically, so now that we've done the classification, this accuracy is of course not 100%, right? So we wanted to do what are the errors our system committed, the model has committed, so that we can improve it further, right? So what we did is basically we picked a few misclassified samples, right? 100 of them, right? And we manually went through those samples, and then we noticed a few interesting patterns wherever our classifier made a mistake, right? What was the pattern, right? Why did the classifier make a mistake? So these are 4 different patterns which emerged. So first one is this one. The same which we have spoken earlier. Basically, there is not enough context around hateful or bad words. And yeah, the second, yeah, this is I think a common issue. So all of this data is manually labeled, right, by humans. So there are mistakes in the data. So this actually, so tweets the classified correctly uh, were labeled wrongly by the humans. So that's actually, you can actually refine your data using the model further, right? So this is, we also saw that there were mistakes by humans which because of that the label was like, because of that we thought it's a mistake, but actually it was correct. Okay, and then there are certain scenarios, right, where basically tweet is there, but there is a URL, right, which says, okay, which says basically, because when a human was annotating, he or she must have seen that URL, what is the content in that URL, right? But as like we are only doing the text, we're ignoring whatever there in that image which it's pointing to. So we couldn't get the context from this external source, right? So that's why there is another set of mistakes, right? And then I think this is interesting, like I earlier spoke about. So there were plenty of scenarios where basically hate was present as sarcasm, and that's why the model got fooled, because of it doesn't understand sarcasm, right? We didn't train it, we only trained on hate. So that's where there were plenty of, I think, issues around where hate was present as sarcasm. So these were a few things. So basically, the lessons are that we should get context, right? Have enough context is important, and then we should also like tackle such scenarios, right? Probably train hate and sarcasm together. That might help further. Okay. Okay. So yeah. So basically, like I said, right, homophily is birds of a feather flock together, right? So you have common interest, you tend to be friends with each other, right? So here, so homophily was first time was established in real face-to-face groups, right? So there, whenever there were common interests, people formed a strong knit group. So that's how it started with, right? And then the homophily is also studied on social networks, right? People who are similar, they are like friends on social network as well, right? So there's and then it plays a vital role in information diffusion, right? Because see, who I'll be friend with is somebody who's similar to me, right? So then what information goes through me, right, is also determined by what my friends are. So it also plays an important role what information I'll receive. Yeah, so that's another in one of another paper, these guys said that on Twitter there is a high reciprocity. I follow you, you usually follow me back. Why? Because we share the same interest, right? So there is a high reciprocity is because of homophily, right? I started following in the first place because there were common interest, and that's why you again started following me, because there were common interest. So there is a high reciprocity on Twitter because of the phenomenon underneath is homophily. Okay. Okay, so there is a lot of papers around it, information diffusion because of homophily. So there is this, basically this is one important study, right? So they study these two political groups and they were looking at what is the information diffusion, what kind of information one group gets versus another group gets, right? So they were saying all these groups, majority group, they're all like-minded, the minority group all like-minded. So information within the majority group remains within the majority group, right? Whatever is in the minority group, they are not exposed to these opposing ideologies. So because of homophily, right? So in fact, they were looking this Yahoo. Earlier, people used to use this Yahoo instant messenger, right? So that basically to communicate, chat, right? So there were. So if I started using Yahoo, you'll also start using, because we similar, right? So they're saying Yahoo adoption, this Yahoo IM adoption was because of homophily rather than influence, right? I'm influential, I'm using doesn't will not lead you to use it. It is leading you to use because of the homophily, not because of my influence. So influence doesn't matter. Actually, there are a lot of studies when it comes to product adoption. It's not because of influence. When it comes, so viral marketing uses a lot of homophily related uh, information to do the product viral marketing or product adoption. So when you figure out what are my first set of candidates, I want to give the free product so that others will adopt. So it's not just the influence. There's a homophily matters there. So when you're looking at the people for your target campaign, then the homophily is actually important part. Okay, so in fact, this in gaming, especially in the gaming world, right? When people form this guild, right? If there is a homophily, then the guild will sustain longer period. Otherwise, it will not. Similarly, there is on YouTube also there was one study done that if a community which has high homophily is sustained for a longer duration, right? So and on there is a topical homophily, meaning people who are interested in the same topic tend to be friends with each other, especially on Twitter. Okay. Now we'll talk about homophily in hateful speech, right? So what are the, let me ask you. So when I say whether a group is homophilic or not, what will you measure to figure that out? What are the quantities, right? Quantitative values or quantitative metrics you will measure. Any guess?
We have a group and we have to measure
Ah, whether that group is homophilic or not. Let's say, yeah. Let's have, yeah. I mean, given a, not a group, let's say given a bunch of people, is whether that is homophilic group or not, right? Bunch or not, yeah. Sorry. Number of likes post. Okay. No, let's say here only. Yeah, I this group, right? Your group. Whether your group is homophilic or not, right? That's what you would. How would you figure that out?
similar.
Similar, yeah, similarity. How similar is the group, right? What else? Yeah. Yeah, so one gender is basically similarity, right? So they're similar in gender sense, right? So similarity can have multiple things, right? One is gender, of course. Another one is
College.
college, maybe. You want like probably interested same genre of movies, so that could be one. In the same sport, whatever, right? So many things. So that is captures the similarity aspect, right? What is the other aspect? The friendship, right? Are given a bunch of people, are they friends with each other or not, right? So in order to figure out whether this group is homophilic or not, right, we need two things. One is the similarity, another is the familiarity, which is basically, you can say, friendship, right? Are they familiar with each other or not, right? And again, we are saying familiar with each other or not, saying is a binary, but it need not be binary, right? It could be any continuous value, right? The familiarity value, the similarity value. You two are similar doesn't mean that you are totally similar, right? It could be a spectrum, right? So I say you two are similar, 0.5 similar. That means maybe half of the things are similar, half are not, right? So similarly, familiarity can also be defined. Like you have your best friends, then some other friends, and some other friends, right? The familiarity, the edge value, basically, strength of your connections. So, so now in order to figure out homophily, we need familiarity. How to define familiarity and how to define similarity, right? So in the real life, it is easy, or maybe not. So I know you know him, right? So you know we are friends. But then what is that friendship value is hard to put, right? And you're similar, but okay, we are similar, that we can define. So now, but on social media, how do we define similarity, especially familiarity? Still, there is a connection edge between two of you. You know each other, but then again, the question, right? That how familiar you are with each other. Maybe the edge weight will count, but edge weight is always not there, right? So that's where this familiarity definition will come. Yeah.
So, like, so suppose we want to see how two people are familiar, similar. We see the number of posts they both like,
Yeah.
the intersection of their posts they like, divided by the
To-
sum of all the posts.
Total post. Yeah. Yeah. That could is one way, right? But that need not be universal way, right? So like there could be multiple ways to define similarities on social networks, right? Any other guess? Any on social network? How do we define similarity?
Modularity is less, we can see it from the community or the clustering coefficient. We can use this to find similarity.
That's for familiar. Similar, yeah, but similarity. Let's say two of you sitting together there. How do you tell that you are similar? Similar meaning your interests are similar, right? You're doing the same things, right? So like he said on social media, let's say I am liking, you're also liking the same post, he's also liking the same post. Maybe both of you are similar, right? That is one way to define. Or maybe the topics you're posting, they're same, right?
Hashtag they follow or whatever.
Hashtag they follow, right? So there are like actually plethora of ways to define similarity. There's no standard, universally accepted way. People use multiple ways depending whatever information they can get, right? Whatever is available. So that's how homophily similarity is defined. So here we'll basically talk about what are the various ways we can capture similarity. Yeah, please.
So what is the extent of similarity or familiarity required? Like how many similar characteristics?
Yes, so there's also again not there's no how many concept, right? It's basically quantity, right? So you and he are similar maybe in, let's say, 90% similar, right? So you can compute the similarity between two of you. And how do we compute? Is basically we have to again measure some characteristics, right? A set of characteristic. The set of characteristic will depend on what context, right? Whatever information we can get. So whatever attributes we can get for both of you, right? So gender we can get, college we can get, maybe whatever you have, right? Whatever data we can have for both of you. Then we can define similarity based on those attributes or characteristics.
So I'm in a book reading club
Ah.
and there are multiple people across and on. So the only similarity is we like to read books.
Yes.
And other than that, there's nothing similar. Everyone's of different ages and different fields. Everything's different.
But that is okay, yeah. So that's what I'm saying. There's no, it's not that, it's not that you have to be at least 90% similar or that similar, right? It's just a relative definition, right? So you should be, there is at least one common interest, right? Because of which you became friends, right? Because all of you loved reading books, you became friends, right? So this says that common interests lead to, like birds of a feather flock together, right? Leading to become friends with each other. Does that answer or? Yeah, okay.